For the last problem, the induced EMF is, again, using Faraday's law, the rate of change of the magnetic flux with respect to time. And for a solenoid, we know that the flux is given by mu naught, the number, n times A times the current. And keeping in mind that the first three terms, u naught, n, and A, are constant, this becomes mu naught n A di dt, or the change in current with respect to time. And these values are now all known. So 4 pi times 10 to the minus 7. We can use this Weber per amp meter unit for mu naught. You'll find out that in this chapter, and a lot of the chapters in this semester, you can use different units depending on what your end goal is. Little n, if you remember, is the turn per unit length, so this is 500 turns per meter. The area was 4 centimeters squared, so 4 times 10 to the minus 4th meter squared, and then the change in current is 100 amps per second. This will give us minus 25 times 10 to the negative 6 Webers per second, which is the same as minus 25 times 10 to the negative 6 volts, or negative 25 microvolts. Now for part B, we know that from the symmetry of the situation that the integral of E dotted with dl is path independent. So it doesn't matter which direction we integrate the loop around, it's going to give us the same value, and that value is going to be given by the absolute value of, it's going to be 2 pi r times E, right? 2 pi r being the circumference around the loop, E being the electric field. And we know that the induced EMF is the same as the integral of E dotted with dl. So the EMF is going to be 2 pi r over times E, which means that E by itself, the electric field, is the induced EMF over 2 pi r, 25, 10 to the minus 6 volts over 2 pi times the radius of 2 centimeters. And this gives us about 2.0 times 10 to the minus 4 volts per meter.